I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the cyclic extensions from the field theory of Msc Part 2nd, Semester 4. Definition of cyclic extension. Let E be a Galois extension of E. Then E is called a cyclic extension of F if G of E by F is a cyclic group. If G of E by F is a cyclic group. For example of cyclic extensions, if omega W is the primitive pth root of unity and the splitting field of x is to p minus 1 over q is q of w is equal to E, say, then E is the Galois extensions of q. Therefore, G of q of w by q is isomorphic to Zp star, and Zp star is a cyclic group of order p minus 1. Therefore, Q of W is a cyclic extensions of Q. Lemma about these cyclic extensions, theorem about this cyclic extension. Let F be a field of non-zero characteristic P. Then for every positive integer K, the mapping summation K of F into itself defined by pi k of x is equal to x raised to p raised to k for all elements x of F is an embedding of F it is into itself. The mapping pi 1 of x is equal to x raised to p x raised to p is called the Phobinious endomorphism. Proof. Consider map pi k from F to F defined by pi k of x is equal to x raised to p raised to k for all x belongs to F. Now we have to prove that pi k is well defined. Let xy belongs to F so that x is equal to y, x raised to p raised to k is equal to y raised to p raised to k. Therefore, pi k of x is equal to pi k of y. Hence, pi k is well defined. Now claim that we have to prove that pi k is injective. Suppose that pi k of x is equal to pi k of y, therefore x is to p raised to k is equal to y raised to p raised to k. Therefore x is to p raised to k minus y raised to p raised to k is equal to 0. X minus y raised to p raised to k is equal to 0. X minus y is equal to 0. Therefore x is equal to y. Therefore pi k is 1 that is pi k is injective. Therefore pi k is an embedding of F into itself for every positive integer k. Next lemma about cyclic extensions. Let E be a finite extensions of F. Suppose F from G of E by F to E star is equal to E minus singleton 0 as a property that f of sigma eta is equal to sigma f of eta into f of sigma for all sigma eta belongs to G is equal to G of E by F. Then there exists alpha belongs to E star so that f of sigma is equal to sigma of alpha inverse into alpha for all sigma belongs to G. The mapping F in the hypothesis of the lemma is called crossed homomorphism. That is proof. For all eta belongs to G, f of eta belongs to E star. Therefore, so f of eta is not equal to 0. Thus, if summation of f of eta of b is equal to 0 for all b belongs to E star, then by the Dedekind lemma, f of eta is equal to 0, which is not true. Hence, there exists b belongs to E star such that alpha is equal to summation of f of eta, eta of beta, eta of b is not equal to 0. Then for any sigma belongs to G, we get summation of sigma of f of beta, sigma of beta b, eta of b is equal to sigma of alpha. Then by using sigma of f of beta is equal to f of sigma inverse into f of sigma eta, we get summation of f of sigma inverse f of sigma eta into sigma eta of b is equal to sigma of alpha. But sigma eta, so that eta belongs to G, is equal to eta, so that eta belongs to G. Hence f of sigma inverse is equal into summation of f of eta, eta of b is equal to sigma of alpha. Therefore f of sigma inverse into alpha is equal to sigma of alpha. Therefore alpha sigma of alpha inverse is equal to f of sigma for all sigma belongs to G. Hence the proof. Lemma about cyclic extensions. Let E be a finite extensions of F and let G is equal to G of E by F be a cyclic group of order n generated by sigma. If W belongs to E such that W dot sigma of eta, sigma of W into sigma square of eta, W dot sigma raised to n minus 1 of eta, W is equal to 1. Then there exists alpha belongs to E star such that W is equal to sigma of alpha into alpha inverse. Proof by lemma. We need to define f from G to C star so that f of sigma is equal to W for some sigma belongs to G and f is a crossed homomorphism. Define f from G to star as follows: f of I D is equal to 1, f of sigma is equal to W, and f of sigma raised to I is equal to sigma raised to I minus 1 of W, sigma of W for 2 less equal I less equal n minus 1. We have to prove that f is a crossed homomorphism, that is f of sigma eta is equal to sigma f of eta into f of sigma. Let sigma raised to I, sigma raised to j belongs to G. Then if I plus j is equivalent to 0 modulus of eta n, then f of sigma I into sigma j is equal to f of sigma raised to I plus j is equal to f of sigma raised to n is equal to f of I d is equal to 1. And also sigma raised to I, f of sigma raised to j, f of sigma raised to I is equal to sigma raised to I, sigma raised to j minus 1 of W dot sigma of W is into sigma raised to I minus 1 W dot sigma of W is equal to sigma raised to n minus 1 of W, sigma raised to n minus 2 of W dot sigma of W is equal to f of sigma raised to n is equal to 1. If I plus j is not equal to 0 modulus of n, then f of sigma raised to I into sigma raised to j is equal to f of sigma raised to I plus j is equal to f of sigma raised to r is equal to sigma raised to r minus 1 of W into sigma raised to r minus 2 of W dot sigma of W into W. I plus j is equal to qn plus r, where r less than n, r is not equal to 0. Now consider sigma raised to I, f of sigma raised to I, f of sigma raised to j is equal to sigma raised to I, f of sigma raised to j minus 1 of W, sigma raised to j minus 2 of W dot sigma of W dot is equal to sigma raised to I r minus 1 of W into sigma raised to r minus 2 of W dot sigma of W is equal to f of sigma raised to r. Hence f is a crossed homomorphism. Therefore using the lemma of 3.3, there exists alpha belongs to A star such that f of sigma is equal to sigma of alpha inverse into alpha. Therefore, W is equal to sigma of alpha inverse into alpha. Hence, the proof. And this is